Hi there, welcome back to my channel. In this video, we'll dive into a crucial application of the depth-first search algorithm, which is the topological sort. Now, familiarity with the depth-first search algorithm is essential before understanding this algorithm. If you need a refresher on the fundamentals, I have included a link to my depth-first search video in the description below. So let's first try to understand what are the use cases for a topological sort. In a given semester, a college presents a range of courses for students to choose from, such as Introduction to Programming, Discrete Mathematics, Data Structures, Algorithms, Databases, Compilers, Formal Languages, Computer Organization, Single Variable Calculus, and Multiple Variable Calculus. However, students are not free to select courses at random, as certain classes have prerequisites that must be completed before enrollment. For example, prior to enrolling in the Discrete Mathematics course, students must first complete the Introduction to Programming course. The Data Structures course has a prerequisite, which is Discrete Mathematics. In turn, the Data Structures course serves as a prerequisite for Algorithms and Databases. The compiler course has three prerequisites: formal languages, computer organization, and data structures. Lastly, the multiple variable calculus course has a prerequisite to the single variable calculus course. As the next step, let's try to represent the courses and their prerequisites as a directed graph. What you see here is a directed acyclical graph, which is disconnected. Here, the nodes in the directed graph represent the courses, and the directed edges between nodes tell us which course has to be done before the other. So what if we have to find a valid order to complete all these courses? Now that's where the topological sort algorithm can help us. A topological sort can be applied to directed acyclical graphs of this kind, giving a valid order for completing all the courses. It is used mainly when tasks or items have to be ordered, where some tasks or items have to be completed before others can. Some other examples of topological sort are scheduling jobs, finding compile time build dependencies, or finding a cycle in a graph. So let's see how we can go about implementing topological sort. We will use the depth-first search traversal algorithm to determine a valid order in which the courses must be completed. I have included the link to the depth-first search video in the description if you need a refresher. So the gray color here indicates that this node has not been discovered during the traversal. Once the node is discovered, the color changes to orange. So discovered means that we have reached a particular node in our navigation process, but we have yet to explore all the paths originating from that node. And once we have examined all paths originating from that node, we can say the node has been explored and the color changes to green. At this point, we can add it to the list in which we are tracking the order. We can start at any arbitrary node that is undiscovered or colored gray. So let's start with formal languages. We'll mark it as discovered. The formal languages course is connected to compilers, so we'll navigate to it. Compilers is not connected to any course, so we will mark it as explored. Since compilers is explored, we'll add it to the list where we are tracking the valid order. We will be inserting nodes in the list from right to left. We backtrack to formal languages and it is not connected to any other course, so we'll mark it as explored and insert it into the list. The next random course we'll select is multivariable calculus. Multivariable calculus is not connected to any node, so we will mark it as explored and insert it into the list. The next arbitrary course that we'll select is Introduction to Programming. That course is connected to discrete math, so we'll navigate to it. Discrete math is connected to data structures and we will navigate to it. Data structures is connected to two unexplored nodes, algorithms and databases. We can navigate to either one of them, so let's just navigate to algorithms. There is nowhere else to navigate from algorithms, So we will set it as explored and insert it in the list. We'll backtrack to data structures. The next unexplored node is databases, and we will navigate to it. Since there is nowhere else to navigate from databases, we'll mark it as explored and insert it into the list. We backtrack to data structures again, and the last node it's connected to is compilers. But compilers is already explored, so we'll skip navigating to it, which is indicated by the dotted line. At this point, we can mark data structures as explored and insert it into the list. We backtrack to discrete math, mark it as explored and insert it into the list. We backtrack again to introduction to programming, mark it as explored and insert that into the list. Moving on, we have two unexplored nodes, single variable calculus and computer organization. So let's select computer organization. The only course it is connected to is compilers, and it is already explored. So we'll skip navigating to it, mark computer organization as explored and insert it into the list. The last unexplored node is single variable calculus. It is connected to multi-variable calculus, which is already explored. So we'll skip navigating to it, mark single variable calculus as explored and insert that into the list. With that, we have reached the end of the topological sort. By using this algorithm, we have successfully generated a valid sequence of courses that a student can take. It's worth noting that the order may vary based on the selection of source nodes. However, the key takeaway is that the resulting order will always be valid. And that is the beauty of this algorithm. So let's now review the code for topological sort. But before we do that, can I please request you to give this video a thumbs up and please subscribe to my channel? I will highly appreciate any feedback. Please share it in the comments section to help me enhance the quality of my content. The course graph can be represented as an adjacency list hash map. In this representation, the key corresponds to a course and the associated value is a list of courses to which it is connected. To further clarify, the key represents a prerequisite and its value is a list of courses for which it is a prerequisite. If you would like a refresher on graph data structure and its various representations, please be sure to check out my video on graphs that I have linked in the description. So this hash map will be parsed as an argument to the topological sort function that I will review next. Now let's examine the code. The initial step is to declare a variable named order to track the topological sort order. Next, the topological sort function will accept the hash map named graph as an argument. In Python, the keys method extracts the keys of the dictionary and we convert that into a list to get our list of courses. We then initialize a dictionary called nodes color where the key is the course name and its value is set to gray to indicate its undiscovered state. For each course in the list, we'll run a DFS on it only if its color is gray. Our DFS function accepts the course name, nodes color dictionary and graph dictionary as arguments. The first thing we'll do is set the nodes color to orange to indicate that it's discovered in the traversal process. And then for each connected course in the graph, we'll recursively run a DFS on it only if its color is gray. Then we'll insert the course at the beginning of the list, which is the 0th index. We'll also mark the course as explored. Finally, we'll return this order that we just created from the function. I have added this code to GitHub and the link is in the description. Please do check out the code when you have some time. Let's go over the time and space complexity. The time complexity of topological sort is similar to that of a DFS, which is O of V plus E, where V represents the number of vertices or nodes and E represents the number of edges in the graph. That's because we are traversing all the nodes and edges. Since we are recursively running DFS on each vertex, the space occupied by the function called stack will be O of V. So that's it for this video. Thank you so much for watching. I look forward to seeing you in my next video. Goodbye.